Okay, welcome to another Astronomy Short OpenStax. Here we'll be looking at Chapter 24, Black Holes and Curved Spacetime. If you recall in the last module, we talked about the death of stars, of high-mass stars, and we said that they interface in a supernova, resulting with a neutron star. While for high-mass stars, typically anything over about 3 solar masses, though, the faith or the plot thickens, they actually become black holes, what we call stellar black holes. And so we'll talk a little bit about that. Let's first, though, talk about introducing general theory of relativity, or more importantly, we'll talk about some of the effects with gravity. And so Albert Einstein's theory currently supports our best understanding of gravity. And it's important for us to discuss gravity when we talk about objects with high matter, and even in these next sections when we get into dark matter and dark energy. So when we're in an elevator, if we're stationary, our weight will remain the same. But if when we start moving downwards, we'll see that our weight actually goes lighter, or going upwards, it gets heavier. And if we were to fall into a free fall, if the rope would snap, we would appear that there is actually no weight, and so it would appear that there's no gravity in that sense. And so we sense this difference typically when the elevator tends to accelerate, when there's a change in speed. So you might be in your car, you're driving along in the car, and if you throw your phone up in the air, it comes right back to your hand. You don't sense that you're moving in the car, the cell phone's moving, any of that. It's just kind of you guys are moving together, right? You don't really feel that. But if the driver presses on the brake, you're going to push forward. You're going to feel that difference now. Or likewise, if you're at a stoplight and they press on the gas too hard, you're going to jolt backwards. So when there's a change in speed, which is acceleration, we tend to notice those differences. And so this leads us with the principle of, or the equivalence principle of gravity when we're in free falling here. If two people were to descend into a bottomless pit and they were throwing a ball back and forth, that ball, if they toss it to one another, it would appear from their vantage point that it would go back and forth. But in reality, gravity is tugging down on all three of them. So that ball would actually arc downwards. Okay? This is similar to, again, if you're in that car with your cell phone and you toss it up in the air, technically that cell phone is not going straight up and down. It's in a car going 50 miles an hour, so it's actually going up and forward. And when you throw it, you're going 50 miles an hour and you catch up to it to actually catch it. But from your vantage point, you don't notice that. So this theory of with relativity has a lot to do with our vantage point, and then the effects of gravity as well. So similarly, we have those influences. Light is actually influenced as well. And light is influenced a lot by gravity. And so we could see those direct relationships when we observe light beams. So we talk about the fabric of space-time as a sheet. And again, space and time are intertwined together. You can't really talk about one without the other. When we talk about position, you tell someone, I'm going to meet you at the corner of Clark and Carson on the third floor. So you give three positions, an X, Y, and Z axis. And then you also tell them at, 8 o'clock. So you tell them where, and then an actual point in space, and then you also give them a time frame. And so space-time, when we talk about it, since we're talking about positions of objects typically, it makes sense to talk about them together. They're actually one in a whole intertwined. So this sheet here represents the fabric of space-time. And imagine an ant that's walking along it. Now, if we were to put some type of weight in there, say like a softball or something, it'll make a crease in there. And so that ant would have to walk down in that little crease and then walk back up to continue on its path. So that crease, that weight there, that crease that's made is actually a better explanation of what gravity is. Gravity is a warp in the fabric of space-time, and everything has to travel along that path, including light. So when we observe light, we're able to observe the influence that gravity has on it fairly easily. So these are some strange ideas here. Well, what do we have to test for these relativity here? Again, everything is observation, right? Experiments here. And, we actually see that. Here's, again, another illustration better of the fabric of space-time. And if we have a star or so, say the sun, and we have some object here, okay? So a planet orbiting around. What actually it is that planet, if it's rolling fast enough, it's going to go down in that crease and it's going to get stuck in that loop, going around and around and around. And that's really what gravity is. So when we talk about the Earth, orbiting around the sun, it's actually because it's in that warp or that fabric of space-time. And we could detect for that. Larger mass stars are going to make larger warps in there, and they'll have a bigger gravitational influence. We see this directly when we look at stars. We look at their apparent direction, and when we look at stars close to the sun, we sometimes detect that the light is coming from a slightly different angle. And so that shows that when that light path goes through, the sun is actually warping a bit and it curves that light coming towards us. We also see this again with radio waves as well, communications to distant satellites. It takes some time for it to actually go down, dip, and then come back up. So there'll be a delay, and we could calculate that delay with the mass of the sun as well. So everything travels on this fabric of space-time, including items from the electromagnetic spectrum. And we notice that light waves, they take extra time to climb from deep holes, so things would have higher gravitational influences there. And so they have that gravitational redshift. So time passes more slowly for things that are closer to a larger gravitational pull. So close to a black hole, right around the edge, which is called an event horizon, we detect that time will actually end up going by slower. So in that fabric of space-time, when you have an object going down or getting bent, influenced by that, again, it not only influences space, but it also influences time as well. So here's an image illustration of a black hole. And so the event horizon is actually on the upper end here. This is kind of the point of no return where you can't see beyond that, where it would be extremely dark. And down at the bottom over here is what we would consider a singularity. So picture a black hole on this fabric of space-time, but instead of putting, a softball or a bowling ball, you're putting like a pellet that weighs the size, that weighs, about the weight of, or has the mass of, say, a truck. So it resembles infinite mass in minimal space. That's kind of what a singularity is. So a black hole becomes this bottomless pit. A star that has a lot of mass at the end of its life, when it becomes unstable and gravity takes over and compresses it, all of that amount of mass just kind of collapses onto itself. Right? It creates that warp in the fabric of space-time, and it becomes a black hole, which think of it as a bottomless pit. So a light beam that ends up traveling along this path will never reach the bottom to be able to come back up. So in a sense, when it goes in, what we're going to see is that the light disappears in a sense, and it just becomes extremely dark in the center. So in reality, what this looks like more is as we have more and more, light beams coming in from all directions or so, the event horizon actually is kind of the point of no return. So once something goes beyond that, we don't end up seeing it any longer. And so really from our vantage point, this would end up just appearing complete void. And that's what we consider the black hole, the darkness there. So nothing could actually end up escaping it. So nothing on the electromagnetic spectrum. So even if you had a walkie-talkie, someone on the inside, that wave would get sucked up by that gravitational pull. And so a definition of a black hole is pretty much an object whose gravity is so powerful that not even light could escape it. And so some of these massive stars, that turn into these supernovas, right, they make a black hole if enough mass falls into the core. It just collapses within itself. And what's created is what we call a singularity. So gravity crushes all matter into a single point known as that singularity there. The event horizon of a black hole that's about 3 solar masses would be the size about of a neutron star, which we said was about the size of a city, so about the size of Long Beach or so. And so the gravitational tug on a black hole is extremely, extremely immense. So as a black hole would, form, you would have it kind of attracting everything towards it. Gravity, right, would start pulling everything towards it there. But once you actually have a black hole, the gravitational pull around it is so strong that the difference of gravity on your foot and your head would be extremely noticeable, and you would kind of get stretched out, kind of like a spaghetti noodle. And really, you would get shredded if you were to try to go any further. Your matter would just rip apart into its actual atoms. Right now, the Earth pulls harder on your feet than your head, but we don't notice it as much because it's not that big of a difference. And so we could see light paths from any object, right, releasing, going out into each direction. However, for something with large gravity, those light curves would curve back around towards it, creating that darkness that we get on a black hole. And so Carl Schwarzschild here gets credit for the coming up with some of the calculations for that and determining the size of a non-rotating black hole. And so again, coming up with the three solar masses, anything beyond that or stars will turn into a what we consider a stellar black hole. And the tidal forces, and so those tidal forces would be more gentler near a supermassive black hole because the radius would be much larger. So if it's compacted more, right, we're going to have more influence on that. We could look also at binary systems. When we look up at the night sky, we know more than half of the stars are binary systems. And it's helpful to look at binary systems with black holes because if they're stealing material, we can't see the actual black hole itself, but we could see the accretion disk around it. And we could see how fast particles are going around there, what actually happens around it, very close to it. So binary systems are very helpful for understanding black holes here. And then also we have evidence of black holes merging together. And when two black holes merge together, they create, it's one of the strongest gravitational impact, or one of the largest kind of impact since we think like the Big Bang, and it'll create these gravitational waves, slight detections or slight waves that we could actually detect very subtly, and we've been able to detect that. Ultimately, when we start looking at, we'll talk more about black holes in the center of galaxies. There's supermassive black holes at the center of galaxies. When we talk about the structure of the universe, we have to understand how galaxies behave and how they tend to gather, which ultimately means that we're studying how supermassive black holes merge and how they end up to attract each other gravitationally. So the plot thickens a bit more with black holes with supermassive black holes. We'll talk more about that in the next section. But this is just kind of a quick overview. And again, it's kind of the another ultimatum of how high mass stars, their ultimate fate. But we really push this towards this cosmology section in Module 4.